Hello everyone. Let's start learning my all-time favorite topic, Newton's laws of motion. As such, there are only three laws to be understood, but the implication is enormous. So I suggest you listen to every example very carefully. Any one of them can appear in your next NEET paper. So let's start. First of all, let's talk about the first law. The first law simply says that anything in state of rest or uniform motion will remain so unless some net external force acts on it. So anything in state of rest or uniform motion will remain so unless a net external force acts on it. Now, what is the meaning of uniform motion? When a body moves, we have defined a quantity called velocity. Now, when I talk about the quantity velocity, it's a vector quantity. So as to completely define velocity, we need to define its magnitude as well as its direction. If the magnitude of velocity, which is the speed, changes, we say that the velocity has changed. If the direction of velocity changes, we say that the velocity has changed. So once more, velocity is a vector quantity. When I say that I have defined velocity of a particle, it means that we have defined its speed as well as the direction of motion. If any one of them changes, then the velocity should change. Now, anything in state of rest or uniform motion will remain so unless a net external force acts on it. It means that if no external force will act, then the velocity will remain constant. It means that if no net external force acts, the body will keep on moving in the same direction with the same speed. The velocity will remain constant. Hence, if the net force on a body is zero, then the rigid body moves with a constant velocity. Okay, this is the first law. A question simply based on first law. As seen from the ground frame, can any object move on a curved path without application of force? Can any object move on a path like this as shown in figure without the application of any force? The answer is very simple. If the particle moves on this path, this means that the direction of velocity must change. The particle might move with a constant speed on this path, but if the direction of motion is changing, we are saying the velocity, which is a vector quantity, is changing. So right here at this position, let's call A, the direction of velocity will be here tangentially. At this point, the direction of velocity will be here tangentially. At this point, the direction of velocity will be here tangentially. At this point, direction of velocity here tangentially. Since at all points, the direction of velocity have to be tangential to path. If a body moves on such a curved path, its direction of velocity will continuously change. As its direction of velocity will continuously change, you need a force for that. So, answer is, if a body moves in curved path, its direction of speed changes and a force is required to change the velocity. You can't change velocity of a body without applying any force. That is the Newton's first law. Now let's talk about second law. The second law says that the net external force acting on a body is directly proportional to the rate of change of momentum with respect to time. The net external force acting on a body is directly proportional to rate of change of momentum with respect to time. So you can write the net force acting is directly proportional to dp by dt, rate of change of momentum with respect to time. Our choice of units is so beautiful that the proportionality constant here, if I say that force is proportional to dp by dt, so you can write F equals to some constant time dp by dt. The choice of units is such that this proportionality constant becomes 1. So we say that the net external force acting on a body is equal to rate of change of momentum with respect to time. Apart from the SI system of unit, in some other system of unit, you might not get the proportionality constant 1. So we get the proportionality constant 1 for the SI system of unit. So F equals to dp by dt. This is the instantaneous force. The force acting on the body at any particular instant equals to the rate of change of momentum with respect to time at that instant. But sometimes we need to find the average force. So from just like, we say that velocity equals to rate of change of position with respect to time. Yes. And average velocity is total displacement by total time taken. On the same guidelines, I will say that If the instantaneous force is rate of change of momentum with respect to time, then the average force has to be equals to the change in momentum upon the change in time. How much the momentum has changed upon how much time it took for this momentum to change. Okay. Now, just by looking at F equals to dp by dt, we can say two more things. Just like using V equals to dx by dt, we can say two things. The slope of xt graph gives velocity. The slope of xt graph gives velocity, and the area under velocity time graph gives the displacement. On the same guideline, just by looking at this equation that F equals to dp by dt, I can say again two things. First, the slope of momentum time graph gives force. The slope of momentum time graph gives force. So on the momentum time graph, if you get a straight line, it means that at all points the slope is constant. It means that the force is constant. If on the momentum time graph you get a growing curve towards momentum, then you will say, sir, going from A to B to C on this curve, the slope is increasing. So if this is the momentum time graph, the force on the particle must be increasing. So the slope of momentum time graph gives the force. The second thing which we can say just by looking at this equation is that, sir, the area under the force time graph gives us the change in momentum. The area under the force time graph gives us the change in momentum. So let's say the force time graph looks like this. And they ask you, let's say this time is T1, this time is T2, this time is T3. They ask you, what is the change in momentum of the particle from time equals to T2 till time equals to T3? So you will say, sir, from time equals to T2 till time equals to T3, the change in momentum is nothing but the area under the force time graph. I will just find out this shaded area, and that will be the change in momentum. So let's see further. First thing we need to understand is the definition of momentum. I have been saying the net external force acting equals to rate of change of momentum with respect to time, but we need to define momentum. So momentum is a very simple quantity. First thing you need to keep in mind, momentum is a vector quantity. So we say that the momentum of a particle of mass m is given by its mass times velocity. Mass is a scalar. Velocity is a vector. And actually, mass is a special type of scalar which is always positive. Mass is a special type of scalar which is always positive. Now see, when I multiply this scalar mass to the velocity vector, I get the momentum vector. And mass can never be negative. So can I say that the momentum of a particle will always be in the same direction as its velocity vector? The momentum vector of a particle will always be in same direction as the velocity vector. Yes, because you are multiplying a positive scalar to a vector to get the momentum vector. So both will be parallel vectors. It's just that the magnitude of momentum will be mass times the magnitude of velocity. So easy. Let's continue. So momentum is a vector quantity, nothing much here to learn. Just remember, momentum is a vector quantity equals to mass of the particle times its velocity. Let's take an example. If a mass of 2 kg moves with velocity of 2 I cap minus 3 j cap plus 5 k cap meter per second. So mass is 2 kg, velocity is given. Definitely they will ask me momentum. Determine the momentum. So I know the mass, I know the velocity, I need to find the momentum. Momentum is simply mass times velocity vector. So you will say momentum equals to mass times velocity vector. Mass is 2 kg, velocity is 2 I cap minus 3 j cap plus 5 k cap. So you get 2 times of 2 I cap minus 3 j cap plus 5 k cap. That becomes 4 I cap minus 6 j cap plus 10 k cap. That's all. What is the unit of momentum? Sir, the unit of mass is kg. The unit of velocity is meter per second. So the unit of momentum is kg meter per second. Simple thing. Let's continue. A question. Determine the momentum of system of blocks in each case. So the first case, you have got these two blocks. A block of mass 1 kg going towards right with a speed of 5 meter per second. A block of 2 kg going towards right with a speed of 6 meter per second. You need to tell the momentum of this system. Remember that momentum is a vector quantity. So as to write the momentum of this system, I have assumed the direction towards right as positive. Now how to write the momentum of this system? You will say the first mass has got velocity in positive direction. The second mass also have got velocity in positive direction. When I write the momentum, I will say momentum will be nothing but 1 times plus 5 plus 2 times plus 6, 1 times plus 5 mv every time. 1 times plus 5 plus 2 times plus 6, that becomes 5 plus 12, that becomes 17. Simple. Let's see the next example. If you have got these two blocks, a block of mass 2 kg going towards right with speed of 3 meter per second, another block of mass 3 kg going towards left with speed of 1 meter per second. What is the momentum of this system of masses? So you will say, if you have taken direction towards right as positive, this 2 kg block's velocity 3 meter per second will be treated as positive, while this 3 kg block's velocity of 1 meter per second will be treated as negative. Why? Because sir, this 1 meter per second is in negative direction. We have taken positive towards right. So when we write the momentum of this system, we will write the momentum to be equals to 2 into plus 3 plus 3 into minus 1. So 2 into plus 3 plus 3 into minus 1, that becomes 6 minus 3, that is 3 kg meter per second. So now the third case, we have got two blocks, one of mass 2 kg going towards left with speed of 2 meter per second, another of 5 kg going towards right with the speed of 1 meter per second. In this case, notice that I have taken the direction towards left as positive. If I have taken the direction towards left as positive, this 2 meter per second velocity will be treated as positive, while this 1 meter per second velocity will be treated as negative. So we will say the net momentum of system will be equals to 2 into plus 2 plus 5 into minus 1, 2 into plus 2 plus 5 into minus 1. That becomes 4 minus 5, which is nothing but minus 1 kg meter per second. Simple thing. Let's continue. If the momentum p of a particle changes with time t as p equals to 4t square plus 3t plus 2. Determine the force acting on the particle at time equals to 1 second and the average force acting on the particle from time equals to 0 till time equals to 2. So, momentum is given as a function of time. Yes, you need to find the force at a particular time and you need to find the average force within a range of time. So, what to do? We know that the force equals to the rate of change of momentum with respect to time. So if you differentiate the momentum with respect to time, what you get is the force function. So we can say that F equals to dp by dt. In place of P, substitute 4t square plus 3t plus 2. So you get d of 4t square plus 3t plus 2 upon dt. Differentiation of 4t square gives you 4 times differentiation of t square, that is 4 times 2t, that is 8t. Differentiation of 3t gives you simply 3. So when you do force equals to dp by dt equals to the rate of change of momentum with respect to time, you get that force comes out to be 8t plus 3. Now you know the force at any time t. Now you know the force at any time t. They are asking you force at time equals to 1. So you will say at time equals to 1, force will be equal to 8 into 1 plus 3, that will be equal to 11. Game over. There is one more thing that we have to do in this question. We need to find the average force from time equals to 0 till time equals to 2. What is average force? Sir, average force is nothing but change in momentum upon change in time. So, how much the momentum has changed upon how much time it took for that change in momentum. So, all you need to do is find the momentum at time equals to 2. From it, subtract the momentum at time equals to 0. This gives you the change in momentum upon the time taken 2 minus 0. 2 seconds. So, we will say the average force equals to change in momentum upon the time taken. Change in momentum is nothing but momentum at time equals to 2 seconds minus the momentum at time equals to 0 second. Sir, how to find the momentum at time equals to 2 seconds and momentum at time equals to 0 second? Beta, here they have given you momentum at any time t. They have given you the momentum time function. So you already know what is the momentum at time equals to 0, 1, 2, 3. You just need to substitute t to find the momentum at any time. So when we need to find average force, we need to find the change in momentum upon the time taken. That is the momentum at time equals to 2 minus the momentum at time equals to 0 upon the time gap. Momentum at time equals to 2 will be 4 into 2 square plus 3 into 2 plus 2. Momentum at time equals to 0 will be 4 into 0 square plus 3 into 0 plus 2. So when you subtract these two momentums, you see this part 2 get cancelled. So here you get 4 into 2 square, 4 into 4 16 plus 3 into 2 6, and this part vanishes. So you get 16 plus 6, that is 22. 22 by 2 gives you 11. So the average force from time equals to 0 till time equals to 2 is 11. Moving on. If the force acting on a particle changes with time as F equals to 3t square plus 2t Newton. The force acting on a particle is not constant. The force acting on the particle is changing with time. Determine the change in momentum of particle or the impulse provided by the force. Now see, what is the definition of change in momentum? Sir, we know that force equals to dp by dt. Yes. So we can write dp equals to f dt. Yes. Integrating both the sides, we say that the total change in momentum equals to integral f dt. But this integral f dt is also called impulse. So beta, just remember, impulse provided is nothing but the change in momentum of the body. The impulse provided to a body is nothing but the change in momentum of the body. The impulse provided to a body is nothing but the change in momentum of the body. Simple. Let's continue. So we know that f equals to dp by dt, so we can write dp equals to f dt. Integrating both the sides, we get integral dp equals to integral f dt. So from here we get the change in momentum is nothing but integral f dt, which is also called impulse provided to the body. Now we know the force function. The force at any time t is 3t square plus 2t. We need to find the change in momentum from time equals to 0 till time equals to 2. So beta, in place of force, substitute 3t square plus 2t and substitute the limit from 0 to 2. So what we get here is the change in momentum equals to integral 3t square plus 2t dt and limit from 0 to 2. Lower limit 0, upper limit 2. The integration of 3t square gives me t cube. The integration of 2t gives me t square. So what we get here is 3 times integration of t square dt gives me t cube by 3. 2 times integration of t dt gives you t square by 2. Substitute the lower limit 0 and upper limit 2. So when you do this 3 get cancelled, 2 get cancelled. On substituting the limit, you will get 2 cube plus 2 square minus lower limit 0 cube plus 0 square. Here it should be square by 2. So anyways, the second term becomes overall 0. So the first term gives you that the change in momentum has to be 2 cube plus 2 square. 2 cube is 8, 2 square is 4. So you get 8 plus 4, which is 12. Next problem. If a gun fires n bullets per second, each of mass m, with a speed v, determine the average force by the gun on bullet. So gun fires n bullets per second. Each bullet has a mass m and each bullet goes with a speed v. Determine the average force by gun on bullet. So we can say, if each bullet has a mass m and if a speed v is provided to each bullet, then the momentum provided by gun to each bullet has to be mv. The momentum provided by gun to each bullet has to be mv. Now, every second the gun fires how many bullets? Sir, n bullet. If to each bullet momentum provided is mv, then to n number of bullets the momentum provided will be nmv. So we can say momentum provided to n bullets will be nmv. We know that the momentum transferred per second to the bullets is nmv. Why? Because sir, see, to each bullet momentum provided is mv. Every second we are firing n bullets, so the momentum transferred to n bullets is nmv. The momentum transferred to the bullets per second is the force. So every second the momentum transferred is nmv. So we can say the average force acting on the bullets equals to the momentum transferred to the bullets upon the time taken. The time taken is 1 second and the momentum transferred is nmv. So what you get is nmv by 1. So average force is nothing but nmv. Remember that here n is not the number of bullets. N is the number of bullets fired per second. Fired per second. Okay. N is the number of bullets fired per second. Simple example. Let's move on. If the position time graph of a particle of mass 2 kg is as shown, find the average force acting on the particle from time equals to 1 till time equals to 3. In the graph, I have shown you position time graph of a particle. Your mission is to find the average force on the particle from time equals to 1 till time equals to 3. How to do? So see, average force is change in momentum upon time taken. Yes. All I need to know is how much the momentum changed and in how much time. So sir, the time frame from 1 second to 3 second is 2 seconds. So I know that delta t is 2 seconds. Well begun, half done. All I need to know now to find the average force is change in momentum. So how to find the change in momentum? You need to know what is the momentum at time equals to 3. What is the momentum at time equals to 1. To know the momentum at any instant, you need to know mass and velocity. In the question, they have given you that mass is 2 kg. So as to know the momentum at time equals to 3 and at time equals to 1, what you need is the velocity at time equals to 3 and time equals to 1. And looking at the position time graph how to find the velocity at time equals to 3 and at time equals to 1. So you will say, sir, see, average force equals to change in momentum upon time taken. Average force is nothing but momentum at time equals to 3 minus momentum at time equals to 1 upon the time gap, which is 3 minus 1. Now, to find the momentum at time equals to 3 and 1, we need the velocity at time equals to 3 and 1. And how to find velocity from position time graph? Sir, the slope of position time graph gives the velocity. So we can say to find the momentum at time equals to 3 and at time equals to 1, we need to find the velocity of time equals to 1 and time equals to 3. At time equals to 3, what do you think is the velocity? 0. How do you know? Sir, so easy thing. Sir, from time equals to 2 till time equals to 5, the position of the particle do not change. From time equals to 2 till time equals to 5, the position is constant. The particle is fixed at the same place for these time frame of 3 seconds. If the position of the particle doesn't change, sir, the velocity is 0. So at time equals to 3, established velocity is 0. What can you say about the velocity at time equals to 1? So you will say, sir, from time equals to 0 till time equals to 2. From time equals to 0 till time equals to 2. The slope of the displacement time graph is constant. If the slope of the displacement time graph is constant, it means that the velocity is constant. So the velocity from time equals to 0 till time equals to 2 is constant everywhere. We need to find the velocity at time equals to 1. We can see from the graph in this 2 second time frame, the particle displaces by 4. So in 2 seconds, the particle displaces by 4 with a constant velocity. So what has to be that velocity? So sir, that velocity has to be the change in position upon time taken, that will be 2 meters per second. From time equals to 0 till time equals to 2, the velocity is constant equal to 2 meters per second. It means that even at time equals to 1, the velocity will be 2 meters per second. So we can say at time equals to 1, velocity has to be 4 by 2, that is 2 meters per second. And at time equals to 3, the velocity will be 0 as the slope of displacement time graph is 0. Once you know the velocity at time equals to 1 and at time equals to 3, you can find the momentum at time equals to 1 and at time equals to 3, and that will give you the average force. So we will say further, average force equals to momentum at time equals to 3. At time equals to 3, momentum will be mass 2 into the velocity at time equals to 3, 0. So that becomes 0. Momentum at time equals to 1 will be mass 2 multiplied by the velocity, which is plus 2. So what you get is average force equals to change in momentum, which is minus 4 upon the time taken, which is 2. So you get minus 4 by 2. Minus 4 by 2 means minus 2 Newton. So that will be the average force. So now let's talk further. F equals to dp by dt. This is Newton's second law. Now we know that momentum can be written as mass times velocity. Yes. Now here in the numerator we have to differentiate multiplication of mass and velocity. We have learned while learning differentiation of fx into gx is nothing but differentiation of fx into gx as it is plus differentiation of gx into fx as it is. So differentiation of first function multiplied by second function as it is plus differentiation of second function multiplied by first function as it is. So from the multiplication rule of differentiation, we can write differentiation of mass multiplied by velocity as it is plus the differentiation of velocity times the mass as it is. You can split out these two terms and write as force equals to dm by dt into v plus dv by dt into m. What is dm by dt? Sir, dm by dt is the rate of change of mass with respect to time. Dm by dt is the rate of change of mass with respect to time. What is dv by dt? The rate of change of velocity with respect to time. But the type of particles we are talking about right now, in those cases, the mass remains constant. So if the mass is constant, we say that dm by dt, the rate of change of mass with respect to time, is 0. Because of this, for constant mass system, the first quantity itself becomes 0. So you can write the force acting equals to the rate of change of velocity with respect to time multiplied by the mass. The rate of change of velocity with respect to time is nothing but acceleration. So we can even write F equals to ma. I asked students many a time, what is Newton's second law? And students end up saying, sir, F equals to ma is Newton's second law. No. Newton's second law is the net external force acting is directly proportional to rate of change of momentum with respect to time. In the SI system of unit, we get that F equals to dp by dt. Then we substitute P as mv and using the multiplication rule, write it as dmv plus dvm. For the constant mass case only, this first term, the rate of change of mass with respect to time becomes 0 and we get that F equals to dv by dt times m. So F equals to ma. This thing works only for constant mass cases. Now I will like you to memorize one line which will help us from Newton's law in friction, in circular motion, everywhere. So this one simple line is really important. You might find it too obvious. The line is, the net external force in the direction of acceleration is mass times acceleration. The net external force on a body in the direction of acceleration equals to mass times acceleration. Okay, so if you have a body of mass 5 kg, towards the right a force of 100 Newton, towards the left a force of 20 Newton. We know that as the net force is towards right, it will accelerate towards right, let's say with some acceleration a. We write the equation as the net force in the direction of acceleration. Now, in the direction of this particular acceleration a, what is the net force? 100 minus 20. So the net force in the direction of acceleration equals to mass times acceleration. So 80 equals to 5a and the acceleration of body is 16 meter per second square. Okay. Now let's talk about the third law, Newton's third law. Everyone knows Newton's third law these days. For every action, there is an equal and opposite reaction. But this is the definition which even a 6th class student will say. You are a NEET aspirant. You should know more. So, the complete definition should be remembered as, for every action, there is an equal and opposite reaction. And the action-reaction pair act upon different bodies simultaneously. Action-reaction pair act upon different bodies simultaneously. Let's say there is a person X and there is a person Y. First, X slapped Y, then Y slapped X. People say that yeah, this is Newton's third law. For every action, there is an equal and opposite reaction because X slapped Y, that's why Y slapped X. No, beta, this is cause and effect relationship. Because X slapped Y, that's why Y slapped X. In Newton's third law, both the forces act simultaneously. So at the time when X slaps Y, when the palm of X touches the cheek of Y, force is being applied by the palm of X on the cheek of Y and force is being applied by the cheek of Y on the palm of X. This is action-reaction pair. Action-reaction pair acts on different bodies simultaneously. So let's understand the third law more with one example. Let's say there is a block placed on a table. The block has mass m. The earth will pull the block down with the force of gravity, that will be mg. The table will push the block up with the force of normal. If the block is in equilibrium, then the net force on the block has to be 0. For the net force on the block to be 0, the force of normal should be equal to the force of gravity, right? The force of normal should be equal to force of gravity. Question is, do the force of normal and gravity form action-reaction pair? Majority of students end up saying yes, but let's see, is it right or wrong from the definition? The definition says that for every action, there is an equal and opposite reaction. and the action reaction pair act on different bodies simultaneously. The action reaction pair act on different bodies simultaneously, different bodies. Here, the force of normal and force of gravity act on the same body. If the force of normal and force of gravity are acting on the same body, they can't be action reaction pair. But sir, they are equal in magnitude. Yes, they are equal in magnitude, but they are not action reaction pair. So sir, where is the action reaction pair? First of all, let's think of normal. As the table pushes the block up with a force equals to N, the block pushes the table down with a force equals to N. These two are action reaction pair. Notice that they are acting on different body. Table applies force on block, block applies force on table. Both the forces have same magnitude, both the forces have opposite direction. What is the action reaction force for the force of gravity? The earth pulls the block down and the block pulls the earth up. It sounds weird, right? That the block pulls the earth up, but actually even you are pulling the earth up. The earth is pulling you down and you are pulling the earth up. So the action reaction pair for the normal and gravity are as shown. This normal and force of gravity are not at all action reaction pair. Okay. So now let's talk about momentum conservation. If the net external force on a system is 0, then from the definition of the net external force acting equals to rate of change of momentum with respect to time, we can say that if the force is 0, then the rate of change of momentum with respect to time has to be 0. If the rate of change of momentum with respect to time has to be 0, it doesn't mean that momentum is 0. But if the rate of change of momentum with respect to time is 0, it means that momentum is constant. So let's see. If no external force act on a system of particle, then its momentum remain conserved. If no external force act on a system of particle, then its momentum remains conserved. Let's understand this with one example. Let's say there are two masses, m1 and m2. m1 has velocity v1 towards right, m2 has velocity v2 towards left, and both of them are going to collide. When the collision will take place, m1 will apply force on m2 towards right, m2 will apply force on m1 towards left. Both the forces will have same magnitude, they will act in opposite direction, and they will act simultaneously. Okay. So now, because of the force applied by m1 on m2 towards right and the force applied by m2 on m1 towards left, the momentum of m2 will increase towards right, the momentum of m1 will increase towards left. But since both the forces act and they have same magnitude and they act for same amount of time, the momentum transferred by one body to another body will have the same magnitude, but they will have opposite direction. So both the bodies will transfer momentum to each other of same magnitude but in opposite direction. That's why you can say the net momentum transfer is 0, because this one gave momentum to that one towards right, that one gave momentum to this one towards left. The net momentum is 0 because momentum is a vector quantity. So here we will say during the collision m1 applies force on m2 and m2 applies force on m1, but on the m1 m2 system the net external force is 0. On the m1 m2 system the net external force is 0, as we know that the net external force equals to rate of change of momentum with respect to time, and the net external force is 0, so we can say that the momentum has to be constant. So if after collision m1 and m2 move with velocities as shown, let's say after collision m1 moves with velocity v1 dash and m2 moves with velocity v2 dash. From momentum conservation, we can say that the momentum of the system before the collision has to equal to momentum of the system after the collision. But momentum is a vector quantity. I have taken the direction towards right as positive. So I will write the momentum of this first mass before collision as m1 into plus v1. I will write the momentum of second mass as m2 into minus v2. I will write the momentum of this first mass after the collision as m1 v1 dash, and I will write the momentum of second mass after the collision as m2 v2 dash. So we can do initial momentum of system m1 v1 minus m2 v2 because it has got momentum towards left equals to m1 v1 dash plus m2 v2 dash. This will be really useful in the later chapter when we will talk about center of mass. There we will learn momentum conservation application in great detail. So let's move on. A boy of mass 50 kg is standing on smooth ice, throws a bag of mass 5 kg horizontally with the speed of 2 meter per second. Determine the speed of the boy after throwing the bag. So there is a boy of mass 50 kg. The boy has got a bag in the hand and the bag has got mass of 5 kg. The boy throws the bag with a speed of 2 meter per second. What is the velocity gained by the boy because of this throwing? Now we need to do the question slowly and understand how does the force act. To throw the bag towards right, on the bag the boy will have to apply force towards right. When the boy applies force on the bag towards right, from Newton's third law, the bag will apply force on the boy towards left. The forces will have same magnitude in opposite direction and the forces will act for same amount of time. So whatever momentum is transferred to the bag towards right, the same amount of momentum will be transferred to the boy towards the left. From momentum conservation, we know that the boy must gain a velocity towards left. Sir, how do you know? Simple. Initially, the whole system was at rest. So initial momentum of whole system is 0. Initial momentum of whole system is 0. For the final momentum to be 0, and momentum is a vector quantity, the boy must gain a momentum towards left. That's why I've taken speed v towards left. As such, this is a simple question. So from momentum conservation, we can say that initial momentum should be equal to final momentum. Initial momentum is 50 plus 5 into 0 because the velocity is 0, and the final momentum taking direction towards right as positive will be written as 5 into 2 plus 50 into minus v. So you get 50 into minus v plus 5 into 2. On the left hand side you have got 0. So from here you get 50v equals to 10. If you get 50v equals to 10, that is as good as v equals to 1 by 5 meter per second. So the boy start moving with a speed of 1 by 5 meter per second. Easy. Let's move on. The force of normal. You will see the force of normal in many questions. Just one simple definition to understand it. The force of normal is pushing in nature. The force of normal is pushing in nature and acts along the direction of normal. That's why it's called normal force. It acts along the direction of normal. So what is normal? The direction perpendicular to the tangent. So let's say if two bodies are in contact, draw tangent at their point of contact. The direction perpendicular to it will be the direction of normal. So the force of normal acts along the direction of normal and it is always pushing in nature. So if I call the surface of block as surface 1 and this curved surface as surface 2, the surface 2 will push the surface 1 away from it and the surface 1 will push the surface 2 away from it. The force of normal acts along the normal and is pushing in nature. So let's take some cases of normal force. The first case, a sphere on a flat surface. Now here there is a sphere and a flat surface. Look at the point of contact. If you draw a tangent at the point of contact, it will be nothing but this flat surface, horizontal. And normal has to be perpendicular to this. So now visualize the normal direction. The force of normal acts along the normal and is pushing in nature. So this flat surface will push the block upwards with a force along the normal, and the sphere will push the flat surface downward with a force along the normal. I have drawn these two forces separately. So the force on sphere of normal is along the normal at the point of contact and is pushing in nature. The surface tries to push the sphere up while the sphere tries to push the surface down. Let's see the next case. Let's say there is a ladder placed between a wall and ground. What will be the direction of normal force by the wall on the ladder? What will be the direction of normal force by the ground on the ladder? So here think of the point of contact, think of the tangent, think of the normal. At the second contact point, think of the tangent, think of the normal. The force of normal acts in the direction of normal and is pushing in nature. So when you think of the forces on the rod, the wall will be pushing, let's say with some force N1, and the ground will be pushing, let's say with some force N2. Similarly, from Newton's third law, I can even think of the forces on the wall and on the ground because of this ladder. So I will say on the wall, there will be a force of N1 towards left, and on the ground, there will be a force N2 downwards. What if the wall is not of sufficient length? The length of the wall is less than the height of the ladder. Then what to do? Then you will say, sir, look at the tangent at the point of contact. First point of contact, and look at the tangent at the second point of contact. The normal is normal to tangent. So at the first point of contact, this will be the normal. At the second point of contact, this will be the normal. The force of normal acts along the normal and is pushing in nature. So the force by this wall and ground on the ladder will be N1 along the normal pushing and N2 along the normal pushing. While the forces by ladder on ground will be equal and opposite. If the wall pushes ladder this way, the ladder will push wall with the same amount of force but in opposite direction N1, and similarly the ladder pushes the ground downward N2. Now let's talk about the force of tension. Just like the force of normal acts along the normal and is pushing in nature, the force of tension acts along the length of string and is pulling in nature. The force of tension acts along the length of string and is pulling in nature. Let's understand it from one example. Let's say we have connected a string between a block and ceiling. In which direction the string applies the force on the block? You have done many a question, and I know that you will say on the block the force will be upward. The string pulls the block up. And similarly, the string pulls the ceiling down. The force of tension is pulling in nature. The string is pulling the ceiling, not pushing it. The string is pulling the block up, not pushing it. So the force of tension is pulling in nature and act along the length of string. So if you look at the forces applied by string on the ceiling, it will be downward, and on the block it will be upward. The force of tension is pulling in nature. For the equilibrium of block, here you can say that the force of tension acting on the block should be equal to the weight of the block. So tension has to be equal to mg. Let's see one more example. Let's say there is a kid flying a kite. The force of tension by the string on the kite will be along the length of string and will be pulling in nature. So I have called this tension as T dash. And the force of tension on the hand of the kid flying the kite will be also along the length of string and will be pulling in nature. So just remember, the force of normal acts along the normal and is pushing in nature. The force of tension acts along the length of string and is pulling in nature. Now let's talk about equilibrium. We say that the body is in mechanical equilibrium when the net force on the body is zero as well as the net torque on the body is zero. We will not talk about torque up to rotational, so forget torque for now. For the body to be in mechanical equilibrium, the net force on the body has to be zero. In which direction? In all directions. So if there is a body which has got net force 0, then you will say that this body is in equilibrium. So the force of 20 Newton cancel out 20 Newton, 40 Newton cancel out 40 Newton. Next question. Can a body under mechanical equilibrium has some velocity? Can a body under mechanical equilibrium has some velocity? Answer is yes. You should not think that if a body is under mechanical equilibrium, then the body should be at rest. No. If there is a mass in space moving with a constant velocity and it keeps on moving, when I say velocity I mean vector, okay, there is a mass in space moving with a constant velocity, it keeps on moving in a straight line with a given speed, you say that this mass is in mechanical equilibrium. Because from the first law, as the velocity of the body is not changing, the net external force on it has to be 0. If the net external force is 0, we can say that the body is in equilibrium. So yes, a body which is in mechanical equilibrium can be moving with a constant velocity. We will talk about torque and omega in the topic of rotational. Right now, let's move on. If three forces are in equilibrium, means they cancel out each other vectorially, then we can use Lami's theorem. What is Lami's theorem? Let's say three forces F1, F2, F3 act at a point such that the angle opposite to F1 is alpha, the angle opposite to F2 is beta, the angle opposite to F3 is gamma. So if the vector sum of these three forces is 0, if force F1 plus F2 plus F3 is 0, then we can say F1 by sine alpha equals to F2 by sine beta equals to F3 by sine gamma. When can you apply Lami's theorem? Two conditions. Condition number 1, there should be three forces involved. Condition number 2, the three forces should be in equilibrium. Their vector sum should be 0, only then you can apply Lami's theorem. But I know that students run away from Lami's theorem for the simple reason that it involves higher angles. Kind of, this beta might be 150 degree and students never like sine 150 degree. So the simple thing that you have to understand here is that you can always write sine of 90 plus theta as cos theta. You can always write sine of 90 plus theta as cos theta. So when you will get, let's say, sine 150 degree in a question, do not think of it as sine 150. Think of it as sine of 90 plus 60. And sine of 90 plus 60 is nothing but cos 60, right? And you know what is cos 60. Cos 60 is half. So that makes it easy. So I see students running away from Lami's theorem despite being very, very useful just because it requires high angle or obtuse angles. So for obtuse angle beta, remember this conversion. Now let's see some problems. Determine the tension T1 and T2 in string. So there are two strings and the angles are given as 120, 150. They're asking you what is the tension in these two strings. What is the value of T1? What is the value of T2? Okay. If I look at this point, I know that this point, which is joined to all the three strings, 1, 2 and 3, this point is not at all accelerating anyway. So the net force on this point has to be 0. So assume the tension in the third string to be T3. Assume the tension in the third string to be T3. Now think of the forces acting on this block of mass M. So forces on the block of mass M will be the force of gravity down mg and the force of tension upward T3. For the equilibrium of this block, the force of gravity mg has to be equal to T3. So mg will be equal to T3. Now you know that at this point three forces are acting, which is T1, T2 and T3, and the angle are 120, 150 and 90. The remaining after 120 and 150 out of 360 is 90. From the Lami's theorem, you can say T3 by sine 90 equals to T1 by sine 150 equals to T2 by sine 120. So you can say T1 by sine 150, see, T1 by sine 150 equals to T2 by sine 120, opposite angle, equals to mg by sine 90 as T3 equals to mg, and sine 90 is one simple thing. So this last part becomes completely equal to mg. Now how to find sine 150 and sine 120? I just told you guys, every time you get obtuse angle, think of sine of 90 plus theta as cos theta. So you can think of this sine 150 as sine of 90 plus 60, which will become cos 60. So you can write T1 by cos 60 equals to T2 by cos 30 equals to mg. Now cos 60 is half. If in place of cos 60 you write half and bring it here, you get T1 equals to mg by 2. Cos 30 is root 3 by 2. If you substitute here root 3 by 2 and bring it to the right hand side, you get T2 equals to root 3 mg by 2. So what you get from here is T1 equals to mg cos 60, that is mg by 2, and T2 equals to mg cos 30, that is root 3 mg by 2. Lami's theorem is really useful and you should know how to apply it. So now let's do some problems to understand the force of tension. Find the tension in the string in each case. The first case, there is a block of mass 5 kg hanged through a string and the block is in equilibrium. We should look at the forces acting on the block. On the block there will be two forces, a force of tension due to string upwards and a force of gravity mg, which is 5 into g, take g as 10, so a force of 50 Newton because of gravity downwards. Since the net force on the block has to be 0, For the block to be in equilibrium, tension has to be equals to mg. So tension will be equal to 50 Newton. Simple question. Let's see the next example. In this case, in addition, we have placed one more force downwards. So look at the forces acting on the 5 kg block. So there is a force of gravity 50 Newton downwards. There is this additional force 20 Newton downward, and there is a force of tension upward. Now for the block to be in equilibrium, the force of tension should be equal to the force of 50 plus the force of 20. So you can say for the block to be in equilibrium, the net force on the block has to be 0. If the net force on the block has to be 0, then the force acting in upward direction should be equal to the force acting in downward direction. So you can say T equals to 20 plus 50. So the tension in the string has to be 70 Newton. Let's see the next example. Now, we have applied a force of 20 Newton upwards. Rather than downward, in the last example, we have applied a force of 20 Newton upward. Now, what will be the tension in the string? So again, we will look at the forces acting on the block. There will be a force of mg downward, 50 Newton downward because of gravity. There will be an upward force external of 20 Newton. And there is a tension of T upwards. Again, for the block to be in equilibrium, the net force on the block has to be 0. So the sum of all the forces in upward direction has to be equal to the force in downward direction. So in the upward direction, the force is T plus 20. And in the downward direction, the force is 5g, which is 50. So you can write T plus 20. The net force in upward direction equals to 5g, which is 50 Newton in downward direction. So if you take the 20 to right hand side, you get that T comes out to be 30 Newton. 50 minus 20 is 30 Newton. Now let's see the next example. Let's say we have applied an upward force of 70 Newton. Now what will be the tension in the string? So now, since you know that the external upward force applied is more than the weight of the block. The weight of the block is 50 Newton, but the external upward force applied is 70 Newton, which is greater than the weight. So a string have to apply no force to support the weight. Hence, the string will become loose and the tension in the string will be 0. So the string becomes loose and the tension in the string is 0. Now, let's look at the forces acting on the block. Once the string becomes loose, the force of tension because of string vanishes. So that's why I have not written any force of tension. Now, what will be the forces acting on the block? A force external of 70 Newton upward, a force of gravity of 50 Newton downward. So the net force on this block in upward direction is 70 Newton minus 50 Newton. The net external force acting on a body is equal to the mass of the body times its acceleration. Here we know that as the net external force is in upward direction, 70 minus 50, the acceleration of the block will be in upward direction. And this acceleration of the block can be formed as, you can say that the acceleration has to be the net external force divided by the mass. You know that F external equals to mass into acceleration. So acceleration has to be the net force external divided by mass. So the net external force is 70 minus 50 divided by the mass, which is 5. So you get 20 by 5, which is nothing but 4 meter per second square upwards. Now let's solve the same type of questions. Rather than finding tension, this time we will try to find normal. So the first question. Determine the normal force by the ground on the block in each case. So let's start with the first case. You have a block of mass 5 kg placed on a table. What will be the force of normal on the block? So look at the forces acting on the block. There is an upward force of normal and there is a downward force of gravity. The force of normal is always pushing in nature. That's why this surface is trying to push the block away from it. Right? Now, for the block to be in equilibrium, the net force has to be 0. So the force of normal should be equal to weight. So N has to be equal to 5g. So the normal reaction has to be nothing but 50 Newton. Simple. Next case. Let's say now we have placed an additional force in the downward direction of 20 Newton. It should be obvious to you if you have a block and you are now pressing it from top, the normal will increase, right? But let's write the equation to understand it. So we will look at the forces acting on the block. There will be an upward force of normal because of the surface. there is an external force of 20 Newton downward, and there is a force due to the weight 5g, 50 Newton. For the block to be in equilibrium, the net force on the block should be 0. So the net force in upward direction should be equal to net force in downward direction. So for equilibrium, you can say the net force in upward direction N should be equal to net force in downward direction, that is 50 plus 20. So you can write N equals to 50 plus 20. So N has to be equals to 70 Newton. Simple cases. Let's see the next one. Now, rather than applying the force of 20 Newton downwards, in this case we have applied the force of 20 Newton upwards. And we have this idea, if you have a block of mass 5 kg, its weight is 50 Newton. If you apply some upward force, then the normal should decrease. It should be less than 50. How much less? The external force you have applied. So you should have this feeling that when you apply an upward force, the normal will decrease by 20, and now the normal reaction will be 30. But let's see this from the free body diagram. If we look at all the forces acting on the 5 kg block, there will be an upward force of normal, there will be an external upward force of 20 Newton, and there will be a downward force of gravity which is 50 Newton, 5g downward. For the block to be in equilibrium again, I will say that the net force on the block should be 0. So the net force in upward direction should be equal to the net force in downward direction. So for the block to be in equilibrium, the net force in upward direction N plus 20 should be equal to the net force in downward direction, which is 50. So the normal reaction has to be equals to 30 Newton. Simple. Let's see the next example. Now let's see the next case. Now on the block of mass 5 kg, we have applied an upward force of 70 Newton. 70 Newton is more than the weight. The weight of the block is 50 Newton. 5 kg, 5g, 50 Newton. And the external force applied is 70 Newton, more than the weight. So, because of this external force which is more than the weight, the block will lose contact with the surface and will start moving up. So, as the force is more than weight, the block will lift up. Once we know that the block will lose the contact with the ground, we already know that the normal reaction will be equal to 0. Let's look at the forces acting on the block. So on the block, there will be an upward force of 70 Newton. There will be a downward force of weight. There is no normal reaction anywhere now. We can say that since there is a net upward force of 20 Newton, the block will accelerate up because of this net force of 20 Newton. 70 minus 50, 20. Again, from acceleration equals to the net external force by mass, we can say that the acceleration of the block has to be 70 minus 50, the net force, divided by mass, that becomes equals to 4 meter per cent square. Hence, in this case, the acceleration of the block will be upward equals to 4 meter per cent square. Now, let's do one more case. Let's say we have got multiple blocks, 2 kg, 3 kg, 5 kg, stacked one over the other. Question is, what is the normal reaction by 3 kg on 2 kg? What is the normal reaction by 3 kg on 2 kg? So you can say the normal reaction by 3 kg on 2 kg supports the weight of this 2 kg block. Yes, sir. So the normal reaction has to be equal to the weight of the 2 kg block. So the normal reaction is 20 Newton. Next question. What is the normal reaction by 5 kg on 3 kg? The normal reaction applied by 5 kg on 3 kg supports the weight of this 2 kg plus 3 kg system. So the normal reaction applied by 5 kg on 3 kg supports the weight of 5 kg mass, 2 kg plus 3 kg, 5 kg mass system. So the normal reaction has to be equal to 50 Newton. That's why the normal by 5 kg on 3 kg is 50 Newton. Next question. What is the normal reaction by floor on 5 kg? By this floor on the 5 kg. So you will say the normal reaction by the floor on the 5 kg supports the weight of entire 2 kg plus 3 kg plus 5 kg system. So the normal reaction by the floor on 5 kg supports the weight of 10 kg mass. If the normal reaction by floor on 5 kg supports the weight of 10 kg mass, then the normal reaction has to be 10 into g, which is nothing but 100 Newton. Easy. Now let's do the same cases but for tension. Let's say we have got here 3 blocks, 3 kg, 2 kg, 1 kg, connected by 3 strings. The tension in the 3 strings are T1, T2 and T3. you need to find the three tensions. So first of all, what will be T3 equal to? The tension here, the tension T3 supports the weight of this 1 kg mass. So we can say that T3 has to be equal to 1 into G 10 Newton, right? So T3 has to be 10 Newton. Next, what has to be the value of T2? The tension here supports the weight of 2 kg plus 1 kg mass. Think of 2 kg and 1 kg as system. So the tension here supports the weight of 3 kg mass. So we can say that T2 has to be equal to 30 Newton. Now we need to find out T1. The tension T1 here supports the weight of 3 kg plus 2 kg plus 1 kg mass. So the tension T1 supports a total mass of 6 kg. And the weight of 6 kg is 6g, which is 60 Newton. So the tension T1 here supports the weight of 6 kg mass. So the tension T1 has to be equals to 60 Newton. Now let's do some problems. If 5 people apply force on a block of mass 2 kg and its acceleration is 0. But if 5 people apply force on a block of mass 2 kg and its acceleration is 0, what can you say? That the forces cancel out each other. If the acceleration of the block is 0, it means that the net force on the block is 0. Then, if one person stops applying the force, the acceleration comes out to be 5 meter per second square towards west. If one person stops applying the force, the acceleration comes out to be 5 meter per second square towards west. Determine the force applied by the person. Okay, whomsoever stops applying force, how much force the person was applying. So let's say the 5 people have named 1, 2, 3, 4, 5. From the problem statement, we can say when these 5 people apply force, then the sum of all the forces, as force is a vector quantity, we should add it vectorially. The sum of all the forces equals to 0. Now when one of them stops applying force, right? Say 5th person stops applying the force. So the net force will be equal to F1 plus F2 plus F3 plus F4. And we know that F1 plus F2 plus F3 plus F4 has to be equal to minus F5. And this, the resultant of these 4 forces produces an acceleration of 5 meter per second square on a block of mass 2 kg towards west. So you can say F1 plus F2 plus F3 plus F4 has to be equal to minus 5, and which is also equal to 2 into 5 towards west. The net force acting should be equal to mass into acceleration, and the acceleration is towards west. That's why the net force have to be towards west. Once we know that minus times of the vector F5 is a force of 10 Newton towards west. So we know that minus F5 equals to 10 Newton towards west. So we can say F5 has to be nothing but 10 Newton towards east. Bring the minus from left hand side to right hand side. If minus times F5 vector is 10 Newton towards west, then F5 vector is nothing but 10 Newton towards east. Easy. So let's see the next example. Find the value of F so that the net force in x direction is 0. So there are 2 forces given, a force F, a force of 20 Newton, and the force F acts at an angle of 60 degree with the direction perpendicular to 20 Newton. And you want the net force in x direction to be 0. So we can break down this force F into components. One component of this force F perpendicular to 20 Newton, that will be F cos 60. So F cos 60 and cos 60 is half. And the another component anti-parallel to 20 Newton, that will be equals to F sin 60. Sin 60 is root 3 by 2. So we want the net force to be 0 in x direction. So simply F sin 60 has to be equals to 20 Newton. So break down the forces. The force F into component. F cos 60, F by 2 is one component. F sin 60, which is root 3, F by 2 is another component. For the net force to be 0, along the x direction, F sin 60, which is root 3 F by 2, should be equal to 20. So if root 3 F by 2 has to equal to 20, you can say that F has to be equal to 40 by root 3. Bring the 2 up and the root 3 down, 40 by root 3. Simple. Let's see the next example. Determine the force by sealing on chain if the chain has a weight W. So here in this problem, we have a chain of weight W, which is hinged at 2 points on the ceiling such that the angle made by ceiling with the chain is theta, the angle made by ceiling with the chain is theta. Question is, what will be the force applied by ceiling on the chain? So visualize the free body diagram of the chain. And remember one thing, the force of tension act along the length of string and is pulling in nature. So this chain, which can be thought of as a string, will be pulling the ceiling along its length. Let's say with a tension T, with a tension T. So if the chain pulls the ceiling down, the ceiling will pull the chain up. So the force applied by ceiling on the chain will look something like these two tensions, pulling both the side, and the force will be along the length of the chain. You can break this tension into component. The horizontal component will be T cos theta, vertical will be T sin theta. Similarly, you can break down the other tension also into component. Horizontal will be T cos theta, vertical will be T sin theta. For the chain to be in equilibrium, the net force in horizontal direction as well as the net force in vertical direction should be 0. You can see that these two T cos theta cancel out each other. Since the net force in vertical direction has to be 0, you can say that T sin theta plus T sin theta, the force upward has to be equals to W, which is the force downward. So we can say for equilibrium 2T sin theta equals to the weight of the chain, or T has to be equals to weight of the chain by 2 sin theta. Easy? Let's see the next example. Actually, this is not an example. This is a very important case which you should know by heart, because this is so useful at many places in physics. You will find a string, you will find a mass, and there will be two forces, one horizontal, one vertical. Usually the vertical force is the force of weight, so I have written it as mg, and there will be some horizontal force. It can be electric force or some external type of horizontal force. Now you will have to determine some things here. What will be the tension in string? What will be the angle theta, given that the mass is in equilibrium? So if the bob is in equilibrium, the resultant of tension, weight and the horizontal force is 0. If the bob is in equilibrium, then the net force acting on the bob must be 0. So if we think of the free body diagram of the bob, there will be a force of tension along the length of string pulling in nature. There is a horizontal force F and a vertically downward weight. We can say that the tension force in the vector form plus the external force in the vector form plus the weight in the vector form, the sum of these three force vectors should be equal to 0 as the bob is in equilibrium. Moreover, since we know that the net force is 0, we can break down this tension into component. We can say that the vertical component of this tension will be T cos theta and the horizontal component of this tension will be T sin theta. If the bob is in equilibrium, then the net force in both vertical as well as horizontal direction should be 0. So you can say that T cos theta has to be equal to mg and T sin theta has to be equal to F. So you can write two equations. T cos theta has to be equal to mg and T sin theta has to be equal to the external force F. Moreover, we learned that if multiple forces act on a body and the net force is 0, then the resultant of all the forces apart from one is equal and opposite to that one force. What is the meaning of this? Let's see. Here we can say the resultant of any two forces is equal and opposite to third. So if I ask you, if I find out resultant of this tension and F, what it will be? I can say with 100% guarantee, since these three forces add up to 0, the resultant of tension and this external force F has to be mg upward. The resultant of any two forces have to be equal and opposite to the third forces, then only the net force will be 0. Similarly, what will be the resultant of tension and force of weight? The resultant of these two has to be F towards left. That's why when you add another force of F, the resultant becomes 0. Similarly, beta, the resultant of F and mg has to be equal and opposite to tension. Now using this concept, we can say, if we find out the resultant of F and mg which are acting at an angle of 90 degree, the magnitude of this resultant will be same as the tension. The resultant of F and mg will be equal and opposite to the force of tension. And since these two forces mg and the horizontal force F are orthogonal, are perpendicular, their resultant will be under root of F square plus m square g square. So you can say tension will be equals to under root of F square plus M square G square. Moreover, what will be the angle theta? You can say the resultant of F and mg, let's say, comes out at some angle theta. It has to be equal and opposite, right? So if this angle is theta, this angle also have to be theta. Now think of the weight vector W, think of the external force vector F, and their resultant comes out to be at some angle theta with the vertical direction, which is the direction of weight vector. So you can say that tan theta, looking in this triangle, you can say that tan theta has to be equals to F by weight or F by mg. Moreover, you could have said tan theta equals to F by mg using these two relations as well. Dividing both the side, you can say, if I call this equation 1 and this equation 2, doing equation 2 by equation 1 on both the side, on the left hand side the t will get cancelled, you will get tan theta equals to F by mg. The same thing. Okay, so you should know this simple important result. That's all in this hour. We'll see you guys in the next hour, where we will talk about connected bodies and constrained motion. See you guys. Bye bye. So that's all for now. See you guys in the next hour.